So yeah, I know it's a Lunar Volatiles group, but I was asked to give a talk on some of my outer solar system volatile transport work. So that's what we'll be doing, focusing on some of the moons of Uranus and Charon, the moon of Pluto. And hopefully you'll see throughout the talk that the work is really motivated originally by a lot of the work on the inner planets, including the moon and Mercury. So to start off, just as a reminder of some of the geological context of what we're dealing with here, the basic interior structure of the worlds we're going to be talking about is a solid ice shell, H2O ice shell. I'm going to try and be careful about identifying ice species when I'm talking. Solid H2O crust. Some of these bodies may or may not have a liquid water ocean and then a deeper silicate interior. This particular diagram is for Enceladus. Various flavors of this diagram will apply to the different worlds in the outer solar system. But the main point that I just want to make here is that H2O, for the purposes of this talk, is not a volatile. So we're going to be doing something a little bit different than thinking about H2O in the inner solar system. We're going to be thinking about other kinds of volatiles with higher volatilities that do act as a volatile in some of these very distant worlds in the outer solar system. And in case anyone is skeptical of that concept, we shouldn't be anymore, especially after the New Horizons mission to Pluto, which showed very, very nicely and very beautifully that we can have these other volatiles, other species acting as volatiles. The most spectacular example being the solid nitrogen ice sheet and glaciers on Pluto. There are other examples in some of the bodies in the outer solar system. There's solid nitrogen glaciers, I think, probably on Triton. There's also methane on Pluto and other species as well. So this is the kind of species that we're going to be thinking about. So the two objects we'll focus mostly on are Umbriel, a moon of Uranus, and Charon, the biggest moon of Pluto. So here are some images. All of the data for the Uranian system, all the spacecraft data, I should say, comes from the Voyager 2 flyby in 1986. And all of the Pluto-Charon data, spacecraft data, comes from the New Horizons flyby a few years ago. So here are our two global images of Umbriel and Charon, and the main argument in this talk is going to be that the two features that we see on the top as these pictures are oriented here can be explained through volatile transport of different species through an exosphere, just like we think about on the moon or Mercury, but adjusting some of the parameters and some of the chemistry that we're thinking about. In the case on the left, you'll see a bright annular ring that we'll argue is potentially a permanent deposit of carbon dioxide ice, bright carbon dioxide ice. And on the right, we'll argue that the red region is the sort of leftover products of methane being radiolytically processed into less volatile tholins, as some people call them, over geological time. So before we dive into the two targets and problems specifically, I'd like to just make a couple points. Again, this is all really motivated by originally lunar work and then later on Mercury work that was led and conducted by some of the people on this call, so some other people as well. Lots of groups doing really interesting work on volatile transport on the moon. The physics is all the same. We're going to be thinking about tracking molecules as they travel through an exosphere. So it's all going to be not a collisional atmosphere. It's all collisionless atmospheres or exospheres. Molecules that start at some point on the surface and ballistically hop over the surface according to their temperature and their velocity and their directions. And at some point, these molecules may escape through various processes. And at some point, they may stick around for a long period of time because they're landing in a relatively cold region where they don't readily sublimate. So some of the processes that we think about are these ballistic hops, genes escape, other mechanisms of escape. There are other processes not shown on this particular image that are important on some bodies. Surface roughness is one of them. Adsorption of molecules onto the surface is another one. There are different kinds of loss mechanisms you can think about. When you get into the outer solar system, you have to sort of think about the trade-off between how many processes you want to include and like our current state of knowledge. So for example, we don't have a nice map of surface roughness from a laser altimeter on Umbriel or Charon. So most of the models I'll show for that will be sort of flat topography or sort of a perfect sphere. There's room, I think, for other people or other groups who want to think about those processes and make educated guesses on what something like surface roughness might look like. The other point on this slide to make is everything is really a statistical approach. Like a given molecule, if you're just tracking one molecule, can do things at semi-random. So we always take a Monte Carlo approach where we're simulating thousands and thousands of molecules as they transport across the surface of one of these bodies and through the exospheres of these bodies to understand what percentage of molecules may get lost to space, what percentage of molecules may migrate to a cold trap, and so on. So those are the sort of 2 points I want us to think about moving forward. Even though the physics is fundamentally the same as a lot of the lunar models, there are a lot of important differences. So I have 4 of them listed in sort of subjectively decreasing order of how important I think they are. Obliquity is, I think, the most important or most interesting one to think about. The obliquities of these systems are very high, so their poles get pointed almost directly towards the sun during summer solstice and almost directly away from the sun during winters. So this has fundamental changes. Importantly, there are no permanently shadowed regions on these bodies. So there's no equivalent of the PSRs on the moon. There's no equivalent of the PSRs on Mercury, as much as we think. And so if you want a volatile deposit to stick around for a geologic timescale, you have to be okay with it seeing some sunlight during the year. This also has the effect of, at least interannually, the stable region for volatiles are going to be at low latitudes, not at the poles, because of the high obliquities. If you're interested in seasonal volatile transport, then the winter pole is most stable. If you're interested in longer time scales, low latitudes are going to be relatively more stable. The chemistry is different. We'll talk about carbon dioxide on Umbriel and the other Uranian moons, methane on Charon. These affects the temperatures at which different species are stable at, and the molecular masses, which is important for some of the escape mechanisms. Moving down the list, much greater distances in the outer solar system, so you have lower temperatures, maybe different weights of different loss mechanisms, and lower gravity changes the escape velocity and makes Jean's escape a bit easier if everything else stays the same. So those are some of the factors we need to think about changing. I think this is what could make it interesting for this group, is thinking about how volatile transport changes if you just change some of these factors compared to the moon. So these are some of the things that we'll be working with. So we'll divide the talk into 2 main parts, Uranus and then the Pluto-Charon system. So starting with Uranus, as a little bit of a primer for those who may not be as familiar with the system. These are the 5 big moons of Uranus, meaning the 5 that are big enough to be spheres. There's dozens of smaller ones. This is the distance from Uranus, not to scale. The sizes of these objects on the slides are to scale. So Miranda is the smallest one. The others are a bit bigger. Miranda is the innermost one, and then outward onto Oberon, which is going to be important in thinking about some of the origin of the carbon dioxide, potential carbon dioxide on these objects. So Umbriel is the middle one. Umbriel is the focus, most of the focus of this portion of the talk. This is like the main piece of data on Umbriel, is like this Voyager 2 image. So a lot different than some of the data sets we're used to thinking about on the moon and Mars and Mercury, where we have nice orbiters. We have one flyby in the 80s from Voyager 2. And maybe the feature that most sticks out is this crater Wunda and this bright ring that you see in the crater. So if you look at it sort of from above and try and reconstruct the image, it might look something like this. The crater is something like 100 kilometers in diameter, a bright ring around what looks like a topographic high. I became interested in this feature because I was reading through some of the Voyager two papers, and some studies had proposed, mentioned possibilities for what the bright deposit could be, but there wasn't really a paper I found that really focused on it as the main point. So I thought that was sort of an interesting thing to think about, especially in light of the bright ices that we've seen at Pluto from New Horizons data. I thought it made it an interesting point to revisit. And so the hypothesis that's going to be tested in this portion of the talk is that this bright deposit is carbon dioxide ice. And the motivation behind this, this hypothesis was some Earth-based astronomy observations. So even though we haven't sent a mission to Uranus since the 80s, we do have some new data from really interesting telescopic observations that some groups have been doing. In particular, I'll point to a couple papers led by Will Grundy and Richard Cartwright that have shown detections of carbon dioxide on 3 of the major moons, Ariel, Umbriel, and Titania, negative detections on Miranda and Oberon, and also longitudinal distribution, where there's more detection, more CO2 on the trailing hemispheres, less so, if any, on the leading hemispheres. And this led to this hypothesis that the CO2 is radiolytically produced by particles that get caught up in Uranus's magnetosphere and impinge upon the centers of the trailing hemispheres of these moons. You don't see them on Miranda because Miranda is too small to hold on to its carbon dioxide species. Escape velocity is very low. And then the trend from Ariel to Titania is because of the particle density as you go inside the magnetosphere. And then Oberon is sort of far away from Uranus, so it doesn't get hit by as many particles. So that was a nice idea that explains the patterns that you see in the longitudinal distributions and also the planetocentric distance from Uranus distributions. So what's interesting is that Wunda, that bright feature, is exactly at the center of the trailing hemisphere of Umbriel. So that's what made me think that this CO2 ice idea, we should take it, we should think about it and test it. And so the way we tested it, we don't have a ton of spacecraft observations of Uranus, but we do have the ability to do some volatile transport models. So we had some thermal models that we conducted to simulate the temperatures across the surface, both in space and in time throughout a Uranian year. Voyager 2 did have a single temperature measurement of some of the moons, which is not throughout the year, but it does sort of ground us. It gives us at least one observation to ground us that we should be getting something in the low 80s of Kelvin for the summer solstice with the right latitudes. And then we do ballistic transport models to simulate what happens to CO2 throughout the year as it transports across the surface. So we want to see if CO2 ice could be stable at this location. It's a different problem than Mercury and the Moon because of the high obliquity and different volatile species. And then I think a compelling test also needs to answer why do we only observe this bright feature on Umbriel, and why is it in the shape of a ring and not just like a circle? So here are the results from our thermal model. I won't bore you with all the nuts and bolts details of the code. We've got a paper from 2017 that you can look up if you're interested in that. We make some guesses for the thermal inertia and albedo, which are important parameters. And here's what the results end up looking like. So these are temperatures at 3 different spots on the surface throughout the Uranian year. So the red line is the North Pole, green line is the South Pole, the blue line is the equator. The blue line is thick because those are diurnal variations throughout a Uranian day. And I think there's some things that you can learn just from looking at this plot. The maximum temperatures, and we think maximum temperatures mostly control sublimation because sublimation is such a temperature sensitive process. Maximum temperatures are at the poles during summer solstice. So during northern summer, say, the North Pole is pointed almost directly at the sun for long periods of time. So it's just getting baked in sunlight and experiencing pretty high temperatures. And conversely, during the winters, facing directly away from the sun almost, so it gets much, much colder, maybe all the way down to maybe 20 Kelvin or so, or in the 20s, in the 30s. So that's good for seasonal volatile stability. The plot I showed before considered some properties for regolith, sort of the dark regolith that we see across the surface. We also considered, what if you accumulate enough CO2 ice that you're changing those surface properties? So ice is bright. Umbriel is a pretty dark moon. So there's a bit of a feedback loop. If you can start accumulating bright ice, that makes that location even more favorable for further accumulation. The albedo increases a lot, it becomes a lot brighter. Maybe you can also get a cohesive ice deposit that has a much higher thermal inertia, which will help suppress the maximum temperatures. So here's what some of those results look like. On the left, the red is the temperature results for sort of high porosity regolith, dark regolith that we might expect as sort of the normal surface on Umbriel. And then green is if you get a cohesive, bright CO2 ice deposit. Similar story for the plot on the right. And the main point that I want to make here is if you can get this feedback loop going, CO2 ice can be stable for long geologic periods of time because the maximum temperature just drops like crazy, tens of Kelvin, because of that brightness and potentially because it gets more cohesive if you can form a cohesive ice deposit.
My quick question on the previous slide. Sorry if you said this and I missed it. On the right, what's the difference between the solid line and the dotted line?
Oh yeah, thanks for that. I did not say that, but I meant to. The solid line is the maximum temperature and the dashed line is the average temperature throughout a year.
Oh, gotcha, thanks.
Yeah, so if you increase the thermal inertia, like you might expect, that the two lines come close to each other and the max temperature is not too much greater than the average temperature. Translating that to sublimation, this is sublimation throughout a Uranian year for the case of the porous dark regolith. This is what the sublimation calculation looks like. You get high sublimation throughout a year at the poles. Almost all of that comes from the summers, and relatively low sublimation at the lower latitudes at the equator. If you get bright CO2 ice that's cohesive with a high thermal inertia, that value is orders of magnitude less than anything on this plot, and you can get that stable for pretty long geological timescales. We next want to do the ballistic transport portion, not just the temperatures. So what the temperatures do is they help us figure out what the right velocities are to use. This is chosen semi-randomly, but only semi. The higher temperatures you get, the higher velocities on average you get. On the left plot that shows what some of the velocity histograms look like as a function of the temperature. The dashed line, the vertical dashed line, that's the escape velocity of Umbriel. So if you have greater than that, your molecule escapes and it's just removed from the simulation. And then the plot on the right shows that escape fraction. Note the logarithmic y-axis as a function of temperature. So the higher temperatures you get, faster velocities, and more molecules escaping. So if you put this all together and you do it in sort of a time-evolving simulation where you get CO2 molecules marching through time and you have time steps throughout a Uranian year, this is sort of what the overall flux at different locations across Umbriel looks like. So remember, it's a high obliquity body, so I've put the north and south poles on the sides rather than the top and bottom. If you start with CO2 everywhere, that's the simulation on the left. Poles get depleted of CO2 pretty quickly. Low latitudes accumulate CO2 not as quickly as it's lost at the poles, but still net accumulation at low latitudes. The plot on the right just sort of arbitrarily shows what if you start with CO2 only in the plus or minus in between 50 degrees north or south, just to give an example of what it looks like as you march through time. And the moral of the story here is just CO2 is going to rapidly migrate over the course of a few Uranian years towards low latitudes. So I think, as expected, based on our intuition from the fact that it's a high obliquity body, low latitudes are the better locations for volatile stability over long time scales. If you're interested in seasonal time scales, it's still going to be the winter poles, but over long time scales, things should migrate to lower and lower latitudes. I think we still need to answer the question, why do we only see the bright spot on Umbriel? Why do we see it as a ring in this crater specifically? The idea that we went with here is that Wunda should probably be a complex crater if you just like extrapolate depth diameter relationships from Cassini data from Saturn moons, for example. So here's an example, Dione. It's a moon about the same size as Umbriel. There's a crater in the center of that image about the same size as Wunda. There's a nice central peak that you can see. So the hypothesis that we're testing here is that Wunda is a complex crater with a central peak, and maybe the floor of the central peak is the sort of local location for volatile stability. There's a few effects to take into account. There's sloped surfaces which experience different insolation histories. The rim and central peak provide shadowing during some portions of the year to some parts of the crater floor. And there's also re-radiated thermal emission from the crater walls and the central peak. So I won't walk you through 10 slides of all the trigonometry that we did, but sort of the result of it looks something like this. So we made a best guess at what the crater diameter and central peak width and height might look like based on extrapolating from the Saturnian system. We tried to quantify the shadowing, the re-radiation, the surface slopes, and we came up with a plot that looks like this. So the colors are showing the annual CO2 flux, and you can see the maximum CO2 flux is the crater floor. So the shadowing from the walls and the peak sort of wins out over the re-radiation effects, and it ends up being just a little bit colder. And because of this positive feedback loop, where if you accumulate a little bit of CO2 ice, it gets brighter, I think that can explain why you see the CO2 ice on the floor of this particular crater and not as a sort of continuous circle, because the central peak is a little bit warmer on average throughout the year. As far as why you only see it on Umbriel, I think two of the moons are relatively easy to explain. Miranda, the escape velocity is super low because the mass of Miranda is pretty small. So the CO2 escapes via thermal escape probably pretty efficiently. Oberon is very far out of from Uranus. So if that magnetosphere radiolytic production idea from Grundy et al. And Cartwright et al. Is right, you might not expect CO2 to be produced efficiently there in the first place. Of the three remaining ones, I just like to remind people that we have only observed a third of the surfaces from spacecraft. So we've only observed a third of the surfaces, and we see a bright spot on one of the three. So that might be consistent. So sort of an obvious test of this idea is we might predict that there's CO2 ice on all three of those moons, Ariel, Umbriel, and Titania. But we've just only seen the right part of the surface on Umbriel just by sort of luck of where the images were taken. So this is a good test for a future spacecraft mission, I think. So I'll wrap up the Uranus part. I think the overall evidence for this is CO2 ice, or CO2 has been detected on the trailing hemisphere of Umbriel. This bright spot is right at the center of the trailing hemisphere. It's very low latitude, it's near the equator, so that sort of checks out with where we expect interannual volatile stability. The calculations sort of show that the Uranian system is in the right sort of sweet spot for carbon dioxide volatility. It's warm enough for CO2 molecules to be bouncing around and migrating, but it's still cold enough for them to not just like completely escape, in a geological second. The bright albedo is at least consistent with what we think the albedo of CO2 ice might look like. And I think the complex crater morphology sort of checks out with why the feature looks like a ring. Other ices might not have the right volatility. 80 Kelvin might sound cold, but it's too warm for something like methane. I don't exactly know why a volcanic feature would be quite that bright, although I've heard some people try to make comparisons to the bright Ockertur feature on Ceres, so that may be something that future groups can test. Hibbets et al. 2002 have talked about activation of CO2 on Callisto in the Jupiter system, which I think is possible, but we see this really on the floor of this crater and not so much in the ejecta. So that's why I leaned a little bit towards the the other origin here, although still something that can be tested. So I think the good prediction for future work will be a spacecraft mission looking for these things on Ariel and Titania, specifically our predictions. Miranda, we wouldn't predict to see this because of the low escape velocity, and depending on what origin mechanism for CO2 you believe, maybe not Oberon as well. So moving on to second part to Sharon. And I have Stephanie, my grad student Stephanie's picture here to remind myself to give her credit and say this project that I'm about to present was led by her. So she's one of my grad students here at Purdue. So you can give her all the credit for this. Okay, so a little bit of a primer to Sharon geology. So I see you have a question. I'm trying to read the chat in real time. Maybe if it's okay, I'll get to it at the end. Okay, so here's our global view of Sharon. New Horizons mission returned all this great data. That's the spacecraft in the bottom of the picture. And a quick primer into what we're looking at here. So the middle terrain is called Ozterra. We won't talk about it too much in this talk. It's sort of an ancient, very old crater tectonized terrain. The terrain we see at the bottom is called Vulcan Planitia. This is, we think, our best guess and the favorite interpretation of the New Horizons team is that it's an extensive resurfacing region that you might call cryovolcanism, resurfaced by extensive, something similar to flood basalts maybe, of viscous water ammonia mixtures triggered by a freezing ocean long ago in Sharon's history. There's some debate as to whether it's 2 billion years ago or 4 billion years ago, but something of order billions of years ago. Big cryovolcanic floodplain. And then on top is a region called Mordor Macula that has been proposed to be methane that escapes from Pluto's atmosphere, travels to Sharon, transports to the winter pole, depending on the season, gets trapped at the winter pole and gets radiolytically processed into tholins or less volatile products over time. So for the remainder of this talk, I'm going to be presenting a sort of alternative hypothesis to just the first part of that idea that was led in a paper by Will Grundy. And what we're going to be proposing is that maybe that most of that idea is right, but we're going to be thinking about whether there could be an endogenic source of methane rather than an exogenic source of methane traveling from Pluto's escaping atmosphere. So none of what I'm about to say is going to be a strike against the exogenic idea. I think that's still going to be in play by the end of this talk. But there are a couple of reasons why we wanted to, why we thought an endogenic idea was worth thinking about for the source of the methane. The first is that we took a look at the North Pole in some geologic maps. And we noticed that some of the impact craters that you see in the North Pole seem to superpose this tholin irradiated methane product region and excavate underlying water ice. So that might be suggestive that the red region formed and then at some point stopped rather than was a continuous source all the way to the present day. There's some nuance behind that because it can still be continuous as long as the rates are low enough. Maybe the crater's excavated water ice, but it hasn't been long enough for the red material to sort of reform. So there is a bit of nuance behind that. I think the more interesting point to me is that there are other Kuiper Belt objects where we have good astronomical observations. And I've learned from the New Horizons mission to trust the astronomers and what they're telling us about what they detect on these KBOs. And there are other KBOs that have been proposed to have irradiated methane products detected on their surface that don't have the luxury of orbiting a Pluto-sized object with an escaping atmosphere to draw methane from. So there should be some other way for KBOs to get methane, even if, in the case of Sharon, the escaping atmosphere is fair game. So the idea that we're testing here is maybe one of those other regions that I mentioned, Vulcan Planitia, is the source of that methane. So we have this big region, it's almost half of the encounter hemisphere, where our best guess is that it's a big resurfacing region of you might call it cryovolcanism. Other words that have been used are crustal foundering, but it's something that's been resurfaced. So maybe that provides the source of how you can provide methane from the interior of Charon out to the surface. And once you get it out to the surface and transport it to Mortar or Macula, all the same arguments made in the Grundy et al. Study would hold true about how it gets processed and the timescales over which it gets processed. So the idea that we'll test is that Vulcan Planitia releases a lot of methane from its cryolava. Just like in the Uranus case, just like in the lunar cases, we'll test with a volatile transport model how that molecule migrates over the surface over time. In this case, we'll see that the seasonal aspect is going to be what we'll focus on more than the interannual aspect. And then if your methane can get deposited at a winter pole and stick around for a season, they can get processed into less volatile products and create ultimately the surface features we see today. So the test that we'll present here is going to be focused on the quantity. Does our best guess of how much methane that Vulcan Planitia would produce over its history supply enough methane for this idea to work out? And does enough of that methane get transported to the poles to get processed into these other products? So we need some estimate of the overall methane content. So the sort of base formula that should yield that is the surface area of this cryovolcanic region multiplied by the average thickness, multiplied by how much methane we think could exist in an ammonia water mixture, multiplied by how much methane we think could get degassed. So a lot of these numbers are going to be guesses, but hopefully what you'll see at the end is that it really ends up just being an order of magnitude calculation. So even if we're off by a bit, the arguments that I'm about to make should hold true. Surface area has been mapped by the New Horizons team in Schenk-et-al. and other papers, so we already have that. Methane solubility based on some work that's been done for Titan, something like half a weight percent in water ammonia mixtures. That can vary a little bit depending on conditions in Charon, but it shouldn't stray too much from that 0.5%. And we assume efficient degassing, which could be argued about. So we're just going to assume all the methane gets degassed. And the big unknown is the thickness of this cryovolcanic unit. We don't have something like a ground penetrating radar to see the bottom of the unit. So we have to use some geologic context to figure that out. So Stephanie spent a lot of time looking through a bunch of landforms in this region, Vulcan Planitia. We're thinking about mountains, craters that might be infilled with the cryovolcanic flow, and tectonic grooves. And all three of these types of features should give us some order of magnitude estimate of thickness of the cryo flow. Luckily, we have a topography map produced by Paul Schenk and colleagues based on stereo images from the New Horizons team. So that's what we'll use. Mountains, the idea here is the mountains pre-existed the cryo flow, and the cryo flow sort of flowed around the mountains and created some lobate features, and you can see to the bottom of the flow in this location. So this provides a nice constraint from the topography, going from the top of the surrounding flow to the bottom of the moat. So we're able to do that for a few of the mountains that we see. We spotted a few craters that look like they could be infilled with cryoflow material. The thought here is just cratering is a dominant process in the solar system. Lots of the craters on Vulcan Planitia probably were formed after Vulcan Planitia formed, but it's reasonable to think at least some of them, some of the larger ones could have remained intact from before the volcanism episode. So we saw a few that looked like they had inflow. There are alternate explanations, just to be forthcoming about that. They could be landslides, but we at least considered the possibility that they were inflow from cryolava material, which ends up giving a thickness estimate of something like a few hundred meters. And then there are all these tectonic grooves on the surface, which have been proposed to be cooling fractures as a cryo flow cooled and solidified over time. If that's the case, the depth to the bottom of the fracture should be a minimum constraint on the thickness, because maybe the fracture doesn't penetrate all the way to the flow if some of the flow is still sort of soft and molten at the time the cooling happens, but still gives a nice order of magnitude constraint. So some of these features, some of these individual features can be argued about, but what is hopeful is that they all give about the same answer. They all give about a few hundred meters to 1.5, 2 kilometers in some cases of your average thickness. So the plot on the left is sort of our best guess at the thickness across the unit, Vulcan Planitia. The sort of final answer is the average thickness is a kilometer. There's lots of uncertainty. It could go down to hundreds of meters. It could maybe go up to 2 kilometers. But it's an order of magnitude estimate, and we think 1.1 kilometers is a pretty good guess. That ends up translating to, given our other assumptions about methane solubility and surface area of Vulcan Planitia, to about 10 to the 41 released methane molecules over the course of the eruption. We need to go now to see how many of those molecules actually make it to the poles. Without a volatile transport model, you don't know if all of those molecules get lost very efficiently, or they all get to a cold trap. I'm putting cold trap in quotation marks because it's not a PSR, it's only a cold trap for a seasonal cycle. So we did our thermal model again, this time for Sharon. Temperatures look something like this. It's a similar story as for Umbriel, although they're not quite as extreme. North and South Pole during winters are very, very cold, approaching 20 Kelvin. Equator varies throughout the day, can get as high as maybe 60 Kelvin. North and South Poles during the summer get very hot, at least for the Pluto system, up to maybe 70. And we don't expect methane to be stable at those sorts of temperatures. But for large portions of the winter, methane should, in theory, be stable at the surface at the winter poles. So similar plot to what we showed for Umbriel. Here are the velocity distributions for a few relevant temperatures. For Sharon, we sort of march through in time steps throughout a year. If a molecule surpasses the escape velocity, we just delete it from the simulation. So that's a potential loss mechanism. And otherwise, we choose our velocities randomly from this sorts of distribution. The sort of final answer, if we do a full time evolving simulation, looks something like this. Around 90% of molecules that get sourced from Vulcan Planitia will end up finding their way to the winter pole before they are lost, and then they'll stick around the winter pole until it's no longer winter and that pole is facing the sun. There are a few portions of the year around LSBS 30 and 210 where this probably doesn't happen, but most of the year, 90% of the molecules can find their way to a cold trap. And if you integrate this throughout the entire history of Vulcan Planitia, this ends up being something like 9 meters of methane deposited at each pole. So to convert that into a rate, you need to know the time scale over which Vulcan Planitia formed, which we do not know, but we at least have an upper limit. Can't be more than billions of years, right? Because it's 4.5 billion years old, presumably, like the other objects in the solar system. So over billion-year timescales, you get microns of methane deposition at the poles per Sharon year. If you can emplace Vulcan Planitia relatively quickly in, say, 1 million years, you get millimeters. But even that upper limit, which is the lower limit for the methane deposition rate of microns per Sharon year, that is higher than the number you would need to source these red regions. So the Grundy et al. Paper predicted something like tenths of microns delivery from Pluto's escaping atmosphere, and that ends up being enough to process enough methane into less volatile products. You end up processing about 1% of the upper tenth of micron or so. So our quantity ends up being enough because we're above this sort of magic number of tenths of microns per year. So we think, at least from a sort of quantity of methane, that this endogenic source is plausible. We might start thinking about if there's other tests that we can do other than just sort of this amount of and volume of methane. So we started thinking about other Kuiper Belt objects. I think that's sort of the most interesting place to take this. Pluto and Charon are interesting objects in their own rights. They're also really interesting to think about sort of putting them in context of the rest of the Kuiper Belt and the rest of the large Kuiper Belt objects. So we picked one Kuiper Belt object, Sedna. We picked this one as sort of an extreme end member. Sedna is really, really far away from the sun. Some people don't even call it a KBO. They have other categories for it, like detached objects and things like that. But it's an icy object that's very, very far away from the sun. So far away that basically the entire surface throughout the year is a cold trap for methane. And so the only point I really want to make here is that different objects in the Kuiper Belt have different volatilities for different chemistries of molecules. It's not just like you get to the uranium system and beyond, everything is stable forever. There's sort of nuance and complexities as you march throughout the Uranus, Neptune, Kuiper Belt system. Some objects like Pluto and Charon might have methane only stable during certain times of the year, during certain portions of the surface. Some objects may be cold enough for some of these exotic ices to be stable sort of over the course of their histories. So I think in summary, at least an endogenic source of methane for this red spot on Charon is plausible, at least from a quantity of methane standpoint. After you get past that, all of the arguments from Brent et al. Will still hold. None of this really disproves the idea of the escaping atmosphere. So I think there could be a combination effect. It could be a sort of a hybrid source of both exogenic and endogenic sources. And I think that the fun thing to think about is putting these objects in the context of the greater Kuiper Belt, thinking about how we put this in context and compare it to astronomical observations of other KBOs that other groups have done. So just to wrap up, I'll spend just a couple minutes and then take questions of how I think these ideas might be tested in the future, both with spacecraft missions, but also before we send spacecraft missions. So I'll start with the second project first. Probably not going to see another spacecraft mission to Charon anytime particularly soon. So I think it's worthwhile to think about other ways that we might test this idea. I think that the two best ways, to be honest, are two things that are a little bit outside my own personal expertise, which are astronomy and laboratory experiments. The people who do astronomical observations of solar system objects, I think, have done a really nice job of informing us where and what volatiles exist as best we can tell from Earth on different KBOs throughout the solar system. And so what our work can do with the volatile transport and volatile stability models, it can inform the predictions of that. Which KBOs should we see different species stable, which KBOs might be too warm, things like that. I like pointing out Maki-Maki because Maki-Maki is an object that has detections of irradiated methane on its surface, but does not orbit a Pluto type of object to draw an escaping atmosphere from. The other angle that we can tackle things from, and that groups have done a really nice job of doing, is sort of laboratory experiments. So a lot of the portions I focused on the physics of the transport. I skipped over some of the radiolysis steps, but those are really important in understanding the timescales and the products that methane or other molecules might turn into over time. And there's been some really nice work done by various groups over thermal and irradiation histories that we think are relevant to Kuiper Belt objects, including Charon. I think what my group at Purdue can do is can think about the geophysics side of the equation. So I talked a lot about cryovolcanism. So what we're planning on doing for Stephanie's next project in her PhD thesis is thinking about how you get that cryovolcanism in the first place. How plausible is it to deliver methane from the interior to the surface? We just sort of assumed in our project so far that methane does get delivered to the surface. But I think there's a lot of work we can do with thermal evolution modeling and finite element modeling to test how efficiently you get material transported from the interior to the surface. And the idea we have specifically is, if you look at Charon, the geology is very hemispheric. There's a whole hemisphere, at least on the encounter hemisphere, that is volcanic, and a whole hemisphere that is older terrain. This has analogies to Mars and Enceladus and some other objects. And I think a really interesting hypothesis that some groups have put forward is degree 1 convection. That is convection that happens in the interior of the body, but rather than a bunch of convection cells in the mantle, it's like sort of the whole planet is one big convection cell. So that's why you see a big hemispherical dichotomy. So we're planning on testing that, seeing if there's any plausible thermal evolution scenarios of Sharon that lead to a degree 1 convection. There is some precedent for thinking this might be plausible on icy objects through some papers by Grad et al. And King et al. For Enceladus in Siri. So there's at least hope, but we'll create a test of that. For the Uranus stuff, there is very excitingly to me, there is hope of new spacecraft data, at least in the intermediate future. So I think the most direct thing to do is to just take our prediction that there might be bright ice deposits on Ariel and Titania, but not on Miranda and maybe on Oberon. And I think that's a very direct thing to test with a spacecraft, both with visible images and any sort of spectroscopy instruments that are on board to look for CO2. There's a conference coming up at the end of July that I'm really excited about out in Pasadena, Uranus flagship conference. So if anyone here is going to that, I'll excited to chat with you then. In the meantime, as we're waiting for spacecraft data, the thing that we're doing in our group that Stephanie is leading is Ariel has a bit of a different geology than Umbriel. Umbriel is just sort of a cratered old ancient surface. Ariel has a lot of canyons and tectonic features on it. So just like we did for the complex crater case on Umbriel, she is thinking about the geometries that we might expect with canyons on Ariel, and seeing if canyons could provide sort of the right shadowing and the right geometry to be cold traps. Maybe on Ariel, we don't see it in a ring around a complex crater. Maybe on Ariel, we see it at sort of the floor or the wall of the canyon. So stay tuned for our results on that in the future. So I'll just conclude with this slide. I think we've shown that even if we don't have orbital data like we do at the moon, we can still use volatile transport models and volatile transport concepts to study the geology of some of these icy worlds. It's interesting to think about the different obliquities and different chemistry and what sort of differences those lead to. For the Uranus system, I think we've shown that it's plausible that there's CO2 ice on the surface, and that's readily testable by a spacecraft mission. I think we've got a nice prediction of what moons should and should not have CO2 deposits, if that idea is right. So that'll be a fun thing to test. For Sharon, I think it's at least plausible that an endogenic source sourced the red regions at the poles. And I think the strategy here will be more astronomy observations, more laboratory experiments by groups outside of my own. And in the meantime, we'll work on some of the geophysics and test how volatiles might get transported from the interior to the surface. So yeah, thanks for the invite, and I'll end there and happy to take questions.
Thanks, Mike. That was great. Very cool stuff. No pun intended. And all right, so we have quite a few questions for you in the chat, and I think these might be all that we have time to get through. But if anyone does think of something else, feel free to put it in the chat or raise a hand, and yeah, we'll see how many questions we can get to.
Yeah, I'll start answering a few of them in the chat while people are thinking. This is not in any meaningful order.
Or you could speak to them. Oh, right, yeah. Sorry, I thought you said you were going to start answering in the chat, and I was going to say.
Oh no, yeah,
do
sorry.
That. Yeah,
trying to read through.
Yeah, I misheard.
Yeah, we did think a little bit about impact gardening rate for the Sharon stuff.
Or actually before that, if we go up a little bit, so maybe if we start with Tim's, or do you have a preferred order for answering the questions? If you do,
no, that's fine. I think I missed the first one.
Right. So the first one was Tim Livengood, who asked if you have an estimate for the magnitude of the CO2 atmosphere at Umbriel over time.
Right. No, we do not. That depends on the production rate, of course. All we did was assumed it was low enough to be an exosphere. And the results that I showed assumed that it was not limited by supply. So that at least there was enough CO2 mixed in the regolith in the regolith case where that was not the limiting factor. Of course, as I think the question is getting at, if the production rate of CO2 is sufficiently low or the inventory is sufficiently low, that could matter in the initial conditions of the transport. Yeah.
Cool. And yeah, the next one was the one you started answering. So
Right.
this was Carl Hibbets, who asked about the impact gardening rate and if that might be able to prevent a relatively low exogenous flux from aggregating to form ice.
Yes, I am. We did consider that. So in the Sharon case, in the map, if you just sort of look at poles, it looks like they're. So let me take a step back. That could help us with this idea of the hybrid case and why some regions might look slightly different. So maybe you have impact gardening that keeps things relatively fresh over billion-year timescales. I know some of the laboratory experiment papers have proposed that actually the radiolytic processing sort of history should go from methane to reddish material to eventually blackish material. And it looks reddish if you just look at the images. So one proposed explanation for that is maybe the impact gardening rate is enough to keep it fresh enough to keep it from totally blackening over time, and why it might look red instead of black. It might also help explain some of the differences between what the geology or the surface looks like in the superposed crater cases versus the craters that or versus the regions that are a bit older. And those numbers, I'm blanking on what the actual gardening rate is, but that was taken from some of the New Horizons cratering and impact flux papers that was led by Kelsey Singer.
Awesome. And then next question 3 of 4. So David Goldstein notes that from these moons, for a molecule to escape, it only has to reach the Hill sphere radius. And does that matter to your conclusions about long-term retention?
Yeah, fair enough. So if you're, I think the long term, I think the overall picture still holds because we are retaining so much of the ice, and the amount that we deposit at the poles, even in the case of Vulcan Planitia forming over billions of years, that's sort of the lowest deposition rate case. Even if Vulcan Planitia forms over billion-year timescales, you still deposit enough. You still deposit an order of 1 or 2 orders of magnitude more methane than you need for the processing to be effective and produce some of the less volatile products. So if we make the escape constraint a little bit looser than just the purely escape velocity, as long as we don't fall down all the way from 90% retention to like 0.01% retention, I think the story will still hold.
Great. And Ujwal asks, do you think there are other endogenic species besides methane on Sharon, such as N2 or CO? Are they also cold trapped and photolized? And then second question, do your simulations consider methane being swapped between the poles during equinox rather than being lost altogether? So other species and swapping between the poles.
Yeah, no, it's a good question. We the seasonal stuff, yeah, that was considered, like the simulations run for a full Sharon year, so that includes sort of seasonal swapping. And I should say, by the way, that there's been some other groups that have done volatile transport models on Sharon, of similar flavors, if not exactly the same. including in the Grundy et al. Paper, including in some work led by, I believe, Teolis et al. And there's similar conclusions about effective seasonal transport of this molecule throughout a sharing year. Yeah, photolysis is included. That comes from calculations done in the Will Grundy et al. Paper. It turns out thermal escape just sort of wins out over that. We didn't do N2 or carbon monoxide. That'd be interesting to think about. I noticed there was a paper that came out recently about where the N2 on Pluto comes from. It's on my reading list. I haven't read it yet, but depending on what that paper says, it could be interesting to think about that as a potential outgassing volatile as well. And yeah, going down through the list, this is all current orbital parameters with Pluto and Charon. So certainly, if the obliquity changes over time, that would affect things. From what I understand from the orbital dynamics prediction papers, obliquity will vary a bit over million-year timescales, but it doesn't get out of this sort of high obliquity state. It may go between, I don't remember the exact numbers off the top of my head, like maybe the high 90s to the low 100s, but it doesn't get down to like low obliquity values like Mercury kind of thing. So some of the numbers may change a little bit in past orbital states, but I think the overall story should be true. You know, with the caveat that these orbital dynamics models, you know, even for bodies in the inner solar system like Mars, you know, we don't know that back 4 billion years ago. So, you know, with that caveat aside, as long as it's in a high obliquity state of some sort, you know, the big picture conclusion should hold true, even if some of the numbers change a little bit.
All right, so we are at the top of the hour. So I think we will close there, but before we do, is there anything sorry, I heard this on a podcast and I was like, I should try this out. Like, so before we, you know, dial off, is there anything we didn't ask you that you'd like to comment on?
Oh, yeah, it's good question. Let me think for a second. You know, I think the main thing that I think is interesting is we went to the Uranus system in 1986. We flew by the Neptune system in 1989. There's a lot of great work done from Voyager 2, and then, you know, the community stopped working on these objects for the most part. Not literally everyone, but for the most part, you know, a lot of the community stopped working on these objects, and I think they're worth revisiting even without new spacecraft data. So we just have such a better intuition for these types of objects from New Horizons and Cassini specifically. You know, New Horizons has given us just a nice view into what these exotic ices might look like on these objects. I think Triton especially, which I didn't talk about, there's a big bright feature on Triton that, you know, there's debate on it, but I basically think personally it's essentially a Sputnik Planitia at one of the poles of Triton, and I think we can learn a lot by revisiting that now that we have a little bit of a better intuition from Pluto. And similar story with Saturn and Cassini and the Uranian moon. So, you know, I would encourage people, if they're interested, I think there's work that we can do to prepare for new spacecraft missions even before we get data back. So I'm really excited about this Uranus meeting at the end of July, and see what people have been thinking about.
Awesome. Yeah. I'd be really curious to hear what the Volatiles related findings from that meeting are as well. Lots of interesting moons out there. And on that note, we'll call it a day, but thanks again, Mike, for a great presentation, and thanks everyone for dialing in, and we'll meet again in about a month from now.
Great. Thanks, everyone.